In the last lecture, we saw that bounds can be given on the distribution of a random variable x using its expectation and variance. Specifically, we saw two inequalities. First one is called Markov's inequality, a very simple one which said that given a random variable x, in this case x had to be positive. It only takes positive values, and the probability that x is greater than or equal to a is bounded by expected value of x divided by a. We modified it slightly, applied Markov inequality to a new random variable and got Chebyshev's inequality, which said that the random variable cannot be too much away from the expectation, or the random variable can be away from expectation, which is bounded by the variance of the random variable. So multiple ways to think about Chebyshev's inequality. Today we will go further and solve something called law of large numbers. Just a note, in the literature this is known as the weak law of large numbers. I strongly encourage you to go and look at strong law of large numbers and the difference between strong law and a weak law. We will not cover it in the course, but you can independently read it. This is the first theorem which tells us the intuitive meaning of the quantity expectation. So we have discussed the intuitive meaning of expectation a lot of times. This is the first theorem to formalize it. So do you remember the intuitive meaning of expectation? If we repeat the experiment multiple times, then our average outcome tends to the expected value of x. This was the intuitive meaning. So let's try to formalize it. We will start with a random variable x. We don't know anything about the sample space. What values does it take? It's just some random variable x. That's all we know. If we repeat the experiment multiple times, then I will have many copies of this random variable x. So I will give them names. I will say that the first iteration the random variable is x1, x2, xn. All of these have same distribution as x, because it is the same distribution as same random variable. Not just that, the expectation, variance, everything for xi is same. So expectation of x is equal to expectation of xi for all I equal to 1 to n. Similarly, variance. It's not just expectation variance, the complete distribution is the same. What did we want to bound? We wanted to say that if we repeat the experiment multiple times and take the average, so I will define a new random variable. This is the average of repetition n times. So if I repeat x n times, this is the summation and this gives me the average. And what we want to show is that this new random variable tends to expectation of x as n tends to infinity. So if n is bigger and bigger, then this random variable will be close to expected value of x with higher and higher probability. One thing to remember, to prove this we will need, I should say we will only need that xi and xj, or the correct way to say it would be the family of random variables xi, I equal to 1 to n. These are just x1, x2 up to xn. These are pairwise independent. Generally, when we repeat the experiment multiple times, most of the time we assume that these random variables are mutually independent. But for this law of large number, we only need pairwise independence. This is a weaker condition than mutual independence. This is something which we discussed previously. So, given such a criteria, we have random variable x, there are n copies of it, x1, x2 up to xn, they are pairwise independent. Then we want to show that this new random variable, the average which we have defined, tends to x. I'm sorry, I shouldn't say e to the x, e of x. What could be a way of doing that? Do you remember an inequality which shows that the random variable x should be close to e of x? The answer is not hard. We have only seen two inequalities, and Chebyshev's inequality fits the bill completely. We need to show that x bar is close to ex. But to apply Chebyshev inequality of this, we need two things. We need expected value of this new random variable and variance of this new random variable. Let's start with expectation. It's a simpler question. What is expectation of x bar? This is expectation of 1 by n summation xi. And now just the linearity of expectation will imply that this is e of x. I will give this to you as an exercise. So pause the video and make sure that you can prove this. Given the random variables x1, x2, xn, all of them have the same expectation. If I take their average, expected value will turn out to be the same. This was the easy part. A slightly trickier version is to figure out the variance of this random variable. The new random variable x bar is the average of x1, x2, xn. You might guess that this is equal to variance of x1 plus variance of x2 plus variance of xn whole divided by 1 by n. We will see that this is not correct. Let's go step by step. The first thing is to figure out what happens to a random variable or what happens to the variance of a random variable when we multiply by a scalar. So in this case, I am multiplying by 1 by n. Summation xi, I will deal with it later. But let's say what happens when I multiply by 1 by n. So here, a very simple exercise which you will do, which is that variance of a times x, x is any random variable. We look at variance of a times x, where a is a constant, is a squared times variance of x. Not hard to prove, it will just follow from the formula of variance. Using this, this will become 1 by n square variance summation xi. And again, you might guess that this quantity is summation over I equal to 1 to n variance of xi. This is not correct in general. What we are going to show is that this assumed thing, variance of xi, no, I should write variance of summation of xi, I equal to 1 to n, is equal to I equal to 1 to n variance of xi. This formula holds true if these random variables are pairwise independent, which was the case for us. So this is the lemma which we want to prove, but you have to remember that this linearity is not always true. It is only true when xi's are pairwise independent. This was true for expectation for all the cases, but now for variance this is only true with some condition. So let's see a proof of this. You might want to pause and try the proof yourself also. Anyway, let me give you the proof. We want to find out the variance of summation xi. This is all summations are going to go from I equal to 1 to n. So let's skip the indices And by the formula of expectation, this is summation xi whole square, the random variable whole square, minus expectation of summation xi whole square. There is a summation here. Now, applying linearity of expectation, this quantity can be broken down into two parts. One is when I multiply and I have two indices I and j, they give me the same thing. So then this becomes xi square. And then there are cases when I is not equal to j. In that case, it becomes xi xj. This is only using linearity of expectation. I split this quantity as a summation that you know how to do it and then apply linearity of expectation. This part is when I equal to j and this is the part when I is not equal to j. Similarly here I can divide it into two parts. One is expectation of xi whole square and then the other quantity would be I not equal to j expectation of xi multiplied by expectation of xj. So again the first part will come out because I is equal to j, the second part will come out because I is not equal to j. Now look at these two quantities, this and this. They look similar, but are they the same? And that is where we are going to use pairwise independence. So in the assignment, you will show that expectation of xi xj is actually equal to expectation of xi, expectation of xj if xi and xj are independent. Show the assignment, but this fact will imply that I can cancel out these things. So my equality becomes I equal to 1 to n expected value of xi square minus I equal to 1 to n expected value of xi whole square. Taking the summation common, I get expected value of xi square minus expected value of xi whole square. And this is nothing but the summation of variance of xi. Great. This simplified our life. We know that variance of xi is same as variance of x in our case. So then, remember why we were doing all this? Because we wanted to figure out this quantity, where x bar was the average outcome. We noticed that the constant can be taken out and it has to be squared. Now, substituting this here, we get that the variance is 1 by n variance of x. That's great. So now, for this random variable x bar, we have all the information to apply Chebyshev inequality. We know that this is expected value of x. We also know that variance of x bar is 1 by n variance of x. Applying Chebyshev inequality directly, we get the law of. So it will say that the probability that a random variable x bar. So remember, this is applying Chebyshev inequality. This will say variance of x bar divided by a square. Now just replacing ex bar and variance of x bar, we will get probability of x bar minus ex greater than equal to a is less than variance of x by n square. And this is the weak law. Why are we interested in this statement? First, a reminder, to prove this, we noticed that this family was pairwise. Then only I could prove such a law. The importance of this arises because of this n in the denominator. So this says that as n tends to infinity, probability that my x bar minus ex, this thing is greater than a for any a. Pick any a. There exists a big N such that this probability tends to 0. So my x bar, my average, will be close to the expectation. And this is what we saw when we discussed a demonstration of the normal random variable. There we picked any x to start with, but when we took the averages, we saw that with very, very high probability, we are very, very close to the expectation. That demo is still on the website. You can download the demo and run it again. And you will see that what we see is a manifestation of this law of large numbers. Just a reminder again, this is the weak law, and you can read strong law. In the next class, we will see similar kind of theorem, but it will be much tighter. The parameters will be much better, and but the x will have some restrictions over it. This is called Chern. And because of the way in which it is derived and because of the constraints, it is very, very useful in computer science. And we will see an application.